In this video, we'll go through the solutions to question 2. Question 2 is 4 parts. In part A, it's about basic operations with sets. So in part A, we have a universal set consisting of every rational number x, which is represented as 1 over y, where y is a whole number. Y is a natural number. Then we have 3 sets, A, B, and C. A consists of all those x in the universal set between 1/7 and 1, inclusive of the endpoints. B consists of these 4 numbers, 1 over 2, 1 over 4, 1 over 6, 1 over 7. And C consists of all those x, again implicitly from the universal set, which are natural number multiples of a quarter. So what are we asked to do here? Well, firstly we need to list the elements of the sets A, B, and C. Okay, B is already given, but to interpret these definitions of A and C and determine their elements. And then say what the elements of these 2 compound sets are. Okay, so looking over here at the solutions, so for the set A, we need to look at all elements, all reciprocals of natural numbers that lie between 1/7 and 1, inclusive of the endpoints. So these will be 1, 1/2, 1/3, quarter, 1/5, 1/6, and 1/7. B, well, we were given the elements of B to begin with. C, so all those elements in the universal set which are multiples of a quarter. So this comes down to these 3 numbers here, namely 1 times a quarter, which is 1/4, 2 times a quarter, which is the same as 1/2, 1 over 2, and 4 times a quarter, which is the same as 1, which is a member of the universal set because it can be represented as 1 over 1. Okay, then look at the other 2 sets we're asked for. We are asked for A intersection B. So we look for the elements that are common to the 2 sets A and B. And we see that it is in fact all of the elements of B. 1/2, 1/4, 1/6, and 1/7. Then we want to look, so what's this set here? The second one we're asked for is the union of A and B less C. So we need to form along the way the union of A and B. So that's the set consisting of every element that is in A or in B, and then remove the elements of C. So we're taking all these elements together here, all the ones in A and all the ones in B, putting them all together, but then removing the elements of C. So, well, B, we've already seen that B is contained in A, so we can just focus on the elements listed here for A and just remove those that are listed in C. So we remove 1, 1/2, and 1/4, and we'll be left with 1/3, 1/5, 1/6, and 1/7. So those are the 4 elements of A union B less C. In question B, part B, again on, well, this is focusing on logic now. So we've got the universal set U. We're told that that's the set of all natural numbers N. And we've got this predicate statement here. For all x, the absolute value of x is equal to x. And it wants us to express that in words, so we want to give an English version of that statement. Then we want to negate this statement and express it in symbolic form. And then say, maybe explain a bit, is that negation true or false itself? So here's the, we start off here in the solution with the English version of that statement. So it says for every natural number, its absolute value is equal to its value. Okay. The negation of that, so the negation of this statement is not for all x, the absolute value of x equals x. So that would be the same as saying that because when you when you negate a universal quantifier, it's the same as saying you have the existential quantifier. Then there exists an x in the universal set such that the statement is not true. So there exists at least one x such that the absolute value of x is not equal to x. That's the negation of the given statement in the question. Is this statement true or false? Well, the fact that x is restricted to being in the natural numbers, then this statement here that we're looking at, the negation statement, is itself false, okay? Because all natural numbers are equal to their own absolute value. So there cannot exist such an x such that this inequality is true. Okay, then turning to part C. Part C concerns complex numbers. And you're asked to prove this relationship here. So this is saying that the conjugate of the sum of z1 plus z2 is equal to the sum of the conjugates, z1 conjugate plus z2 conjugate. I'm going to prove this statement for all complex numbers z1 and z2. So this is an argument. Well, what this is assessing here is your knowledge of the definition of a complex number, how to add complex numbers, and what the operation of conjugation is. So you need to get all of these elements correct in your answer. So we introduced two complex numbers, z1 and z2, in real and imaginary, in the form of their real and imaginary components. So we'd let z1 be a complex number a1 plus b1i. z2 is a2 plus b2i, so I is the square root of minus 1, and these parts a2 and b2 are both real numbers. Then the conjugate, okay, so the conjugate operation reverses the sign on the imaginary part. So the conjugate of z1 is a1 minus b1i, conjugate of z2 is a2 minus b2i. So now let's try and prove this equation here, prove this relation. So we begin with the conjugate of z1 plus z2. So we introduce the elements of z1 and z2 here and add them together in such a way that we can see clearly here the real part, a1 plus a2, plus I times the imaginary part, b1 plus b2. Now we're in a position to apply this conjugate operation, which gives us a1 plus a2 minus b1 plus b2 times I. Okay, that's dealing with the left-hand side of the given results. That we then focus on the right-hand side, adding together the two conjugates. Well, the conjugate of z1 is a1 minus b1i, conjugate of z2 is a2 minus b2i, and then we're demonstrating that when you collect together the real and imaginary parts here, you get a1 plus a2, the real part, minus I times the imaginary part being minus b1 plus b2. And what we've shown there is that these two expressions are the same. The conjugate of z1 plus z2 and the conjugate of z1 plus the conjugate of z2. They're both the same. So we proved the required result. The last part, part D, gives us two integrals to carry out, integrals I and j. So we look at I first of all. So this is an indefinite integral. So as for the indefinite integral of x times sine of x. So, well, the way we can proceed here is use integration by parts, using known facts about the derivative and integral of the sine function as well. So in order to do that, we need to prepare the integrand, the function that's integrated here, into two parts, a part u times a derivative of a part v. So u, for us here, u is just the quantity x, and the derivative of v we want to be the quantity sine of x. So that would make v to be the quantity minus cosine of x. And the derivative of u then would just be the constant 1. So applying the integration by parts formula, this integral is going to be the product of u and v, which would be minus x cosine of x, plus the integral of the derivative of u times v. Sorry, minus the integral of the derivative of u times v. So this brings in two minus signs, so it converts to a plus sign, and so this reduces then to the integral of cosine of x. Okay, so the derivative of u is a constant 1. Then we can use the known fact about behavior of the cosine function, that the integral of the cosine function is the sine function. But carrying out that last indefinite integral, we need to include a constant of integration c in our final answer as well. So we get minus x cosine of x plus sine of x plus some arbitrary constant c.